So we have already completed covalent bonding in the last class, right? Hello? Please speak out.
Yes, ma'am.
Yes, ma'am.
Okay. So we have completed covalent bonding. Rion, you were not there. I shared the recording with you. Did you go through it? Yes, Rion. Did you see the recording I shared? Kaveri, even you were not there last week. I shared recording. Rion, I cannot hear you if you're speaking. Okay. You can let me know over the chat if you are able to hear me. Alright, so now we are going to continue with the properties of covalent bonds, of covalent compounds. So covalent bonds are present in covalent compounds. Okay. And we are going to study about them. In the last chapter, metals and non-metals, we studied about the properties of ionic compounds, like ionic compounds are hard, crystalline, then they have very strong interionic forces of attraction, they are soluble in water, they are good conductors of electricity in their aqueous solution or in their fused or molten state. So those were the properties of ionic compounds and they had ionic bond in them. Now the compounds, Kaveri, recording is already sent to you. You are asking me when I'll send you the recording. It's been 3 days. It's been 3 days I shared the recording with the mail ID. Ask your mom to check. Okay? And that's what I think I even messaged your mom to so that you will go through the recordings. Fine, just check it. Fine. So we'll continue. Yeah. So properties of covalent compounds we have to study. Now this paragraph I got from your book. Shruti, read it out. And all of you
Hello.
see in your book. Yeah, Rion, I can hear you.
Yes, ma'am.
Shruti, unmute yourself and read. Shruti, can you hear me?
Yes, yes, ma'am.
So read what is written over the screen.
Yeah. Most carbon compounds are poor conductors of electricity, as we have seen in Chapter 2. From the data on the boiling and melting points of the above compounds, we can conclude that the forces of attraction between these molecules are not very strong. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds does not give rise to any ions. In class 9, we learned about the combining capacity of various elements and how it depends upon the number of valence electrons. Let us now look at the electronic configuration of carbon. The atomic number of carbon is 6. What would be the distribution of electrons in various shells for carbon? How many valence electrons will carbon have?
So you already have answers to these questions. Okay. Now this paragraph is very important. It says that most carbon compounds are poor conductors of electricity. And we have seen that these compounds have covalent bonding. Okay. In ionic compounds, we studied that they were good conductor of electricity. So if they are largely non-conductors of electricity, it means that in these bonding, there is no formation of ions. Ions are not formed in covalent bonding, and that's true also. Okay. That's true also. That there are no ions are formed, and we have already seen when we have studied bonding in covalent compounds, correct? That there are ions are not formed, and that's the simple reason why it doesn't conduct electricity. So this is asked in our test as reasoning questions. Okay, just give me a moment, children. All right. Now, one thing why they don't conduct electricity is they don't form ions. For electrical conduction, opposite charges are required. So ionic compounds were conducting electricity due to the positive and negative ions. Now coming to the melting and the boiling point part. We are seeing that in this data that the melting point and boiling point of the compounds are low. How can we understand they are low? To understand that they are low, we should have idea of some high melting and boiling point. So this low melting, high melting, they are the comparative terms. Otherwise, how will we understand? So all of you, I think you are having your NCERT book with you. In your NCERT book, go to metals and non-metals chapter, page number 48. All of you, go to page number 48 of the textbook. Janvi, over the page number 48, melting and boiling point of some ionic compounds are given. Read the melting
Yes,
point
ma'am.
for the first compound.
Ionic compound NaCl, melting point 1074 and the boiling point is 1686.
Now you compare this value. Look at the melting point and boiling point of sodium chloride and just go below. Next is lithium chloride. Dikshant, can you tell me the melting point and boiling point of lithium chloride?
Yes, ma'am. Lithium chloride melting point is 887 Kelvin and boiling point is 1600 Kelvin.
Hari, tell me for the next one.
CaCl2 melting point 1045 Kelvin and boiling point 1900 Kelvin.
Okay. Now next, Rion is going to tell us for calcium oxide.
For calcium oxide, the melting point is 2850 Kelvin and the boiling point is 3120 Kelvin.
Yeah. Now next, Shruti is going to tell us for magnesium chloride.
It is melting point is 981 and boiling point is 1685.
Yeah. So I have even made a check that all of you are sitting with books or not. And Kaveri, now also I can't hear you. Okay. So if you are able to hear me, Kaveri, you continue. Continue with the session. Whatever is required, put it over the chat. Don't leave the class if my voice is going to you. Okay. Yeah. Now you can see the values. They are in Kelvin. Okay. For sodium chloride, it was 1074 Kelvin melting point. So 1074 Kelvin. What will be the value in degree Celsius? Hari, will you tell us? 1074 Kelvin in degree Celsius?
I don't know.
Oh, you don't know how to convert Kelvin into degree Celsius. Who is going to tell the answer?
Is it minus 273?
See, nobody has unmuted. Yes, it is to subtract minus 273. What else? Kelvin will be converted into degree Celsius. So sodium chloride's temperature will be coming around 801 degrees Celsius. Why am I relating it with this? Because we are more used to temperatures of degree Celsius. Water boils at 100 degrees Celsius and we boil it at our home. So we are able to relate it. So imagine water boils at 100 degrees Celsius and water is a covalent compound. And sodium chloride, the salt we eat, it melts at 800 degrees Celsius. So you are seeing the difference, right? Coming back to our chapter, carbon and its compounds, and the data which you are seeing over the screen, which I have taken from your book itself, textbook page number 59. So here you see there are some compounds, acetic acid, chloroform, ethanol, methane. You are seeing the value like 290 Kelvin. Okay, 290 Kelvin you see for acetic acid. What is this temperature in degree Celsius? Will anyone tell me? Rion is going to tell me.
17.
So 290 minus 273, just 17 degrees Celsius.
Degrees Celsius.
Okay, so it is also lower than our normal room temperature. Like in winters, when the winter begins, we get to this temperature. So this temperature is going to come in another 30 days. So then we will start chilling 17 degrees Celsius and or below if it is going. So now these are having so low melting point. Melting point means changing from solid to liquid state. So acetic acid, it is a liquid. What I want to tell you, it is a liquid. It is present in vinegar. You are going to study in this lesson about acetic acid as a very special compound. And now when we are talking at its melting point is 17 degrees Celsius, it means the temperature we have presently, 29, 30, 31, it is present at as liquid. And when the temperature falls in winters, acetic acid converts to solid state. It is the 17 degrees Celsius which is the freezing or the melting point of acetic acid. Now you can imagine how low is this temperature. All those things which are present in our nature in their liquid state, they have very low melting point. Of course, because they are already present as liquid state, it means their solid state, conversion of solid to liquid is melting, right? So if that liquid, like water at our conditions, water is in liquid state, maybe on some other planet or on our planet, on poles, on the top of the mountain peaks, water is at snow because the temperature is low. So if you are seeing 17 degrees Celsius as the melting point, it means it is a very low melting temperature, and that's why it is present as liquid. And in winters it solidifies also, pure acetic acid. Now boiling point also you see 391 Kelvin. 391 Kelvin, if we are subtracting from 273, what are we going to get? Yes? Please speak out, children. Be active.
80.
No.
118.
118? 391 minus 273 will give us 118 degrees Celsius. So to convert it into vapors, we need to heat it above the boiling point of water. Water boils at 100 degrees Celsius. We have to boil it at 118 degrees Celsius. These are easily achievable temperatures, 100 degree and 118 degrees Celsius. So the reason, now important thing is reason. You look at chloroforms and all. Now see, they are going very low. 209, 156.
Minus 64.
Minus 64, right? Now comment on methane. Methane's melting point they're saying is 90. 90.
Minus 183.
So, yeah, so here is the calculator. You can see 90 minus 273. To look, why it's showing the 60. 90 minus 273 is equals to minus 183. Minus 183 is the melting point because methane in our nature exists as a gas. It exists as a gas. And if you are talking about melting point of a gas, first you should think about its solidification. So you are going to lower the temperature and you are increasing the pressure, which you studied in class 9th, right? Change of state of matter. So when you are lowering the temperature, you are increasing the pressure. By creating conditions, you have to solidify it. So when it is brought to minus 183 degrees Celsius, then it will solidify. And at this point, you can think of its melting. So low melting temperature. What it shows, what is the reason? But when it comes to ionic compound, we are seeing sodium chloride 800 degrees Celsius. Aluminium oxide melts at 2500 degrees Celsius. Just imagine. Okay, so there has to be a reason which I want to tell you. The reason is forces of attraction. In ionic compounds, the forces of attraction were very strong. So shall we conclude that covalent bonds are weak? If we are saying ionic compounds have very strong forces of attraction, and that's why the energy required to break those forces of attraction was high, melting point was high. So in return, the conclusion will come, covalent bonds are weak. But no, this is not the reason. There is a term which you have to understand here. In that chapter also, ionic compound, I insisted to students while teaching. How many of you have remembered? I don't know. It is Hari. Do you want to say something here?
No.
Okay, I saw you unmuting yourself, so I felt maybe you are saying something. So it is not the covalent bond which is weak. It is the intermolecular bond that is weak. Now, what is this intermolecular bond and covalent bond? Must be something confusing for you. For this, I will talk about sodium chloride first, ionic compound, and then I will come back to covalent compound. Sodium chloride, which is very known to you people, so you can easily understand, it has Na plus and Cl minus. Now, this is one formula unit. In actual, sodium chloride doesn't exist just as one Na and Cl, right? So how does it exist? Every sodium is surrounded by chlorine ions, and not just 4. These 4 I can keep on papers.
I'm 6.
6, right? So there will be 2 more chlorine ions. One will be on the back side, another will be on the front, like a 3D structure. Over paper, without creating a mess, I can show you just 4. Now every Cl minus is surrounded by 6 NAs. So Na plus, Na plus, Na plus. Now this is the structure of a crystal of sodium chloride. Now what is important? This one has a very high melting point. Reason? So if I look at this, we studied formation of ionic bond NaCl, and because there is this electrostatic nature, so they are strong bond. That is fine, but what is making higher melting point is, look everywhere. Everywhere it will appear to you as NaCl. Here also NaCl. If you look this way also NaCl. If you look this way also NaCl. So it has same kind of force of attraction with the neighboring particle also. So with the neighbor also, the force of attraction is ionic in nature. It has bonded with, it has given its electron to this chlorine. It has attraction, that ionic forces are there, electrostatic, but it has similar attraction to this one also, because this one is also negatively charged. This Cl minus has similar forces of attraction. So with the neighboring particles also, the force of attraction is ionic in nature. This is called inter-ionic force of attraction. Inter word itself means other. Internet, connecting different networks. International cricket match. India playing with other countries. International, with different nation. Inter-school, different schools. So inter-ionic. So not inside your molecule, we are talking with your neighbors, how you are interacting. So this is about ionic compounds. They are very strong. Now let's think about the covalent compounds. Covalent compounds, they are, for example, let's talk about methane. So inside methane, inside this molecule, 1 carbon and 4 hydrogens are there, and they are attached by covalent bonds. It is not that this bond is very weak. Its interaction with the neighboring methane particle is not very strong. So the CH4 we are having, it's a gas. So if you are having 1 liter of methane gas, unit for the gases for volume is also liter, like liquids. So if you are having 1 decimeter cube or 1 liter of methane gas, amongst these particles, the forces of attraction is not very high. And that's why the melting point and boiling point are so low. One of the example we have for low melting point covalent solid is wax. The candle wax that we burn, so easily we see that wax begins to melt. It's a covalent compound. And we always keep the knob of the petrol in our vehicles secured. We put it very firmly, tightly, we close the knob of the petroleum. We don't keep it open because it quickly changes from liquid to gaseous state. Its evaporation happens very fast. What it shows, bonds are not stronger. That's why it is changing from liquid to the gaseous state. One reason is it catches fire also. Second reason is you are buying so expensive petrol, you cannot just let it evaporate. Why it evaporates? Low boiling point. Then nail polish remover. It's acetone. Acetone is a organic compound. You are going to study ahead in this chapter. You pour little acetone and you can check if this nail polish remover is very common thing in our homes. We never keep it open. You check, you open the first lid, inside there is another one. There is a very tight lid inside it above the main lid we have, so that no particles will evaporate. If you will leave in 1 spoon or something, you leave, you see it will evaporate. So the reason is the intermolecular forces of attraction are not strong. Okay, now you have to move, all of you have to move to page number 60 of the textbook. On page 60 of the textbook, last paragraph is given. Okay, so I want somebody to read that paragraph. Janvi, read the paragraph. Page 60, last paragraph.
Such bonds which are formed by the sharing of an electron pair between two atoms are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule.
Underline
but
this part, all of you. Covalently bonded molecules are seen to have strong bonds within the molecule. This clarity should be there with all of you. Yeah, continue, Janvi.
This gives rise to the low melting and boiling points of these compounds.
I interfered you. Read this statement once again from covalently bonded.
Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are small.
So till here, intermolecular forces are small. Now read, continue.
This gives rise to the low melting and boiling points of these compounds. Since the electrons are shared between atoms and no charged particles are formed, such covalent compounds are generally poor conductors of electricity.
Yes. Make sure that out of these two is coming in your FA3. If your school takes a pen and paper test or in your worksheet, they are going to take this. Why covalent compounds are poor conductors of electricity, or why they have low melting and boiling point. And I hope I have explained you the reason. Anybody, any doubt over here? Any questions to ask? Rion, any question?
No, ma'am.
Is it clear?
Yeah.
Hari, Dikshant?
No, ma'am.
Okay, fine. So, all right, and then we are moving ahead. Okay. Next, we are going to study about uniqueness of carbon. We have talked so much till now that carbon forms 3 million compounds and it outnumbers all 117 elements and their compounds. Something must be special about it. That speciality we are going to start. And in all those points which we are going to study under the speciality or uniqueness of carbon, points like, so in all these points which we are going to study, covalent bonding has a role to play. That's why we study covalent bond before. Okay. Now the first thing or the first uniqueness we are going to see, I have kept written it, tetravalency. Tetravalency, so tetra is a Greek word for 4, and we have already discussed this, that valency of carbon is 4. In its outermost shell you can see there are 4 electrons. So it has valency 4. Now owing to this valency, it can form 4 bonds, as there are 4 electrons available in the outermost shell. Due to this, carbon combines with 4 atoms, and these 4 atoms could be of same element, like you can see methane. 1 carbon combined with 4 hydrogen atoms. They could be atoms of the same elements, or they can also be the atoms of different elements. CF, Cl, Bri. You can see here 4 different atoms are connected. This compound is called bromochlorofluoroiodomethane. Okay? So its name and all is not important to you at this level. At very high level all these comes. Bromochlorofluoroiodomethane and all. So we are seeing the advantage of tetravalency. Now see, this is a maximum valency. Valency can be 1, 2, 3 or 4. So here carbon is able to combine with 4 atoms. So it can give so many varieties. Now see here, carbon has combined with 4 hydrogen atoms. If we simply remove 1 hydrogen atom, because there cannot be more than 4 bonds. There cannot be 5th bond here in carbon. So if we are just removing one of the hydrogen, because getting a 5th one is not possible, and 1 chlorine. This is a new compound. It's called chloromethane. I will give all these names later in the chapter. Now, if we are substituting another hydrogen with chlorine, this is also possible. Now, this is a completely new compound, dichloromethane. You can similarly replace 3rd chlorine, 4 chlorine, and one by one you will get new compound. Now, this is not the end. This is 1 carbon which has shown us all this degree of compounds. We can have 2 carbons now connected, carbon to carbon, and then again join all hydrogens, replace 1 hydrogen, put 1 chlorine. This is all possible. So tetravalency gives carbon a chance to form compound with 4 different or 4 same atoms. Okay, and with that it forms so many compounds. And yes, whenever you see carbon anywhere in any formula, make sure that there are 4 bonds around it. If you are seeing lesser, 3 bonds or 5 bonds, there is something wrong in it. So tetravalency is simply the valency of 4 which carbon has, which makes it special. Next question arises here. Is it only carbon which is showing this tetravalency? Don't we have any other? So there are others also, like silicon. Silicon is also tetravalent. It also has valency of 4. It can form silicon tetrachloride. Now it can be asked to you, any other element than carbon which has tetravalency? So silicon is also tetravalent. So we will write it with red to show that it is also important. Silicon is also, lead also forms, correct. Silicon is tetravalent. Okay. Lead also forms lead tetrachloride. So you should remember this. So if silicon is also tetravalent, why are we talking about so much greatness of carbon? Because carbon doesn't have only this unique feature. There are many others which are adding to its value. So we have begun the first one, that's tetravalency. After tetravalency, the next one is catenation. Now what's catenation? Catenation is the self-linking property of carbon. Now what is the meaning of self-linking? Self-linking is combining with same atom. Or rather, framing it in better words, atoms of same elements when they join to form a molecule, it's called as catenation. For example, phosphorus. Phosphorus molecule, it's polyatomic. We studied in 9th class, right? Formula of phosphorus is P4. So 4 phosphorus atoms have joined here. So atoms of the same elements have joined. This is catenation. Sulfur. Sulfur's formula is S8. 8 atoms of sulfur join in this ring-like structure. S8. So this is atoms of the same element joining to form long chains or ring-like structure is called as catenation. I'll write it down. Catenation is atoms of same elements, or rather catenation is the property. We'll do a little change. Catenation is the property in which atoms of same element join to form long chains or ring structures. Now here, when we are giving examples of phosphorus, sulfur, why are we again studying it in the speciality or uniqueness of carbon? Because when it comes to carbon, carbon can join with so many atoms. Now when I'm saying so many atoms, how many atoms am I going to talk about? Starting from 2 carbon atoms, 2400 carbon atoms can be joined together. So things like plastic bags, polymers, they are made up of carbon, which have chain of some 2400 carbons joining together. So you just imagine, even hydrogen will H join with H, just 2 atoms. Sulfur S with S, 8 atoms. Okay? But when it comes to carbon, carbon and carbon can join with each other right from 2 carbon atoms. We can have till 2400 and 2500 carbon atoms joining together. Why? Why so that carbon can do it and others cannot? Because of the strong covalent bonds. That's the reason. So extent of the catenation depends upon the strength of the bond. So we will not say that the covalent bond is weak. Covalent bond is strong bond, and especially in carbon it is stronger. Why? I will tell you later. So here, extent of catenation depends on the strength of the bond. Stronger the bond, higher the catenation. Okay? Stronger the bond, higher the catenation. Stronger the bond, higher the catenation. Fine? Now, this is not done with the carbon that some 2 to 2400 carbon atoms are joining. When they join, that also they do in some patterns like this. Catenation in carbon happens and carbon atoms join to form straight chain structure. Straight chain, carbon, carbon, carbon linked to each other. One next to each other, forming straight chain. There are 5 carbon atoms if you see in the first structure, 1, 2, 3, 4 and 5, which are linked next to each other. Next, you see that with just those 5 carbon atoms, a branch chain is also created. So 4 carbons are there in one row, and to the third carbon there is a branch. Now what is a branch? Branch should never be at the end. This is a straight carbon chain, and drawing carbon like this is wrong. Always 4 bonds. Okay. So I say to my children, if you are making something mistake in drawing 4 lines around carbon, it's a crime. Don't do the crime in my class. So there should be 4 bonds around it, every carbon, because it's tetravalent. Now, at the 2 terminal carbons, terminal means ending. This is one end and this is the other end. Here you cannot put up a branch that, okay, you joined a carbon over here and you are calling a branch. No. Then it is just a bent. You have just bent the straight chain. So remember the rule for branch chain. It should be attached to the carbon, leaving the ends. Ends, in your higher class, you will be used to say terminal carbon. Terminals are the ends. So you are not supposed to put a branch to the 2 ends or the 2 extremes, either here. So leaving the right or the left end, put it in the middle. This is called a branch. This is possible in carbon. Now this facility is not available in sulfur and phosphorus. Okay, now let's link this way, let's form a branch. No, this carbon is giving this facility. Now carbon also form closed structure, ring structure. So here you can see there are 4 carbon atoms which have formed a ring-like structure. It is possible with 5 carbon atoms also. 1, 2, 3, 4, 5, a pentagonal structure. This is also possible. And now look carefully. Everywhere there are 4 bonds. In this ring structure, carbon is already attached to 2 carbons. So 2 electrons are used up in bonding. So okay, 2 more bonds are possible. Next carbon, joint to 2 adjacent carbons, place for 2 more bonding. Everywhere there will be 4 bonds. So when it comes to catenation also, carbon has 3 possibility: straight chain, branch chain, closed chain. Dikshant, do you want to ask any question related to catenation?
No, ma'am.
Hari, any question? Any doubt in your mind?
No, ma'am.
Janvi?
No, ma'am.
Kaveri, type and tell me if you have any doubt. Just type over there in the chat box. Okay, fine. Rion, Shruti. Rion, any doubt?
No, ma'am.
Shruti?
No, no doubts.
No, ma'am.
Danya, any doubt? You have also joined. All right. So even you don't have any doubt? Fine. We are done with catenation. We have seen 2 points. We have seen catenation. We have seen the tetravalency. Next, third point. Carbon forms strong covalent bond. I already discussed the strong covalent bond point with you. Now we are going to understand what is this strong covalent bond. Carbon forms strong covalent bond. It means between carbon and carbon we are talking about. Carbon bonds with oxygen also with double bond. In carbon dioxide also we have O double bond, C double bond, O. Carbon forms bond with hydrogen also. Carbon and hydrogen forms, it forms methane. So I'm not talking here about that. I'm talking about the bond between 2 carbon atoms. Because if it is catenation happening, so if there are like these hundreds of carbon atoms joining, so it is the strength between their bond, right? They're holding hands with each other so strongly. So there has to be a reason, and that reason is that the covalent bonding is very strong in carbon. Now what is the factor that can make a covalent bond strong or weak? In ionic compound, we studied that ionic forces, electrostatic forces are there which hold them together, the positive charge and the negative charge. We did not even think that what is holding the covalent bonds? Electrons are shared. So what is the force of attraction? That now the two nuclei are placed close by and they have formed a molecule. We have begun talking that chemical bonding is force of attraction, right? So what is that force of attraction nature in covalent bonding? Let's talk about it. Now this is an atom. This is another atom and they are covalently bonded. I'll take the simplest example, that's hydrogen. Scientists also prefer to work with hydrogen because it is very simple. One proton, one electron, not even a neutron. In the middle, we are having the nucleus. What is the charge of the nucleus? Rion. What is the charge of the nucleus of an atom? Hurry.
Positive.
Of course positive. Nucleus have only proton and neutron. That one hydrogen one doesn't have neutron. Even if neutrons are there, neutrons are neutral. So nucleus is positively charged. Okay? And electrons are present. All of you, Rion. Nucleus is positively charged due to protons. Electrons are revolving in the orbits in the shells. Now when a covalent bonding happens, what is holding? If this is example of hydrogen I have taken, these are two hydrogen atoms. So if we are saying that, okay, now the electron will be shared and all, how the electron will be shared, it will be used by both the atoms. So it is something like this. Electron of one of the atom is attracted by the positive charge of another atom. It is attracted to its own atom, that's fine. If it is holding, this electron is going under the control of other nuclei. It is going to move here. It is going to take a path over here. So even this nuclei is exerting a force of attraction. And that is because of opposite charges once again. So the nucleus of the one of the atom attracts electron of the other one. Similar thing happens in the other atom. Electrons of the one is attracted by the nucleus of the other. But there are repulsive forces also. Opposite charges attract or unlike charges attract, but like charges repel each other. So there will also be repulsion. Electron of both the atoms will repel each other. Nucleus of both the atoms will repel each other. So the two atoms, they place themselves at a position where they have maximum attractive forces and minimum repulsive forces. So a balance is created. Otherwise, if there will not be repulsion, the two atoms will fuse with each other. That fusion doesn't happen. There is intermolecular distance. There is distance present between the two atoms. And that is because of repulsive forces. Now we understood the forces in covalent bonds. It is once again electrostatic in nature. Electron of one atom is attracted to the nuclei of another and vice versa. Now what? We want to understand what makes a covalent bond strong or weak. So it is the attractive force of the nucleus which is being exerted on the electron, or the electron which is being shared by the neighbor. It means this force should be attracted till the outermost shell. It should be stronger enough till outermost shell. If the atoms are very big, say for this is these are the two atoms which are going to take part in the bonding. And the nucleus is as usual placed in the middle. Now, this is also having positive charge. Electron as usual is present in the it is present in the inside shell also, but the incoming electron or the outgoing electron or the shared electron, it all happens for the valence shells. Okay. So in which case you think the force of attraction will be more? When the atom is big, then the force of attraction will be more, or when the atom is small? When the atoms are small, then the force of attraction is higher, because as the atom will become bigger, the nucleus will become far from the outermost shell. One point is this. Another point, when there will be more shells inside, bigger atom means there are more shells inside, right? And if there are more shells inside, there are shielding electrons. What are shielding electrons? In these inside shells also, there are electrons present. You are going to study more of this in your 11th classes. Shielding effect will come then. So these electrons are present in these shells. Now electrons are present in this shell also, and these are continuously revolving. They are moving. When they are moving, they are covering the outermost electron from the attractive power of the nucleus. They are shielding, they are covering. So if the atoms are very big, they are participating in covalent bonding, the bonds will be weaker. But if the atoms are smaller, the bonding will be strong. And now when we are saying that carbon forms strong covalent bond, the reason is the carbon has small size. Carbon is not a very big atom, it has small size, and due to small size, it forms strong bonds. Come to page number 62 of the book. Hurry, page 62. There are 2 points given. In the second point, read the last paragraph. All of you look at that paragraph. Yeah.
Again, the bond that carbon forms with most other elements are very strong, making these compounds exceptionally stable. One reason for the formation of strong bonds by carbon is its small size. This enables the nucleus to hold on to the shared pairs of electrons strongly. The bonds formed by elements having larger atoms are much weaker.
Underline it. Things like this go very ignored. A question can be asked, why the covalent bonds formed by larger atoms are weaker? And I'm going to give this in our next test as a question. So if the atoms are large, the distance between the outermost shell and the nucleus is more. So the forces of attraction exerted by the nucleus is less. Hence, the bonds are weak. So I was telling in context to catenation. It shows so much catenation because the bonds form are strong. And it combines with so many atoms, fluorine, chlorine, bromine, iodine, with all it forms very strong bond. If carbon is small, its nucleus can tightly, strongly hold the electrons of the other atoms. Okay? So we will not say that covalent bond is a weak bond. Got this point? Deekshant, any question to ask?
Oh, ma'am.
Dhanya, Janvi, any question to ask?
No, ma'am.
Riyan, understood? Shruti?
Ma'am.
Shruti, is it clear?
Yes, ma'am.
Okay, good, good, very good, children. Now we are going to the next point. Carbon forms multiple bonds. Would anyone tell me what is this multiple bonds?
Like single bond, covalent, single bond, double bond, triple bond.
Yes, very good, Dikshant. Hydrogen, it forms H single bond H. Done. That's it. Oxygen, O double bond oxygen. No O single bond O, no O triple bond O. Nitrogen forms N triple bond N. And coming to carbon, carbon can form carbon single bond carbon. It can form carbon double bond carbon. It can form carbon triple bond carbon. Hey, that's not the bond, the last line. I was putting up a comma. There should be only 4 bonds. That I was about to do a big crime, putting the 5th bond. No. So there are only 4 bonds. Look carefully here also. So there are these 3 possibilities with carbon. So carbon forms single bond. Once again, such a beauty of carbon. Okay. So carbon forms multiple bonds. We are going to talk about multiple bonds later in the chapter when we will talk about hydrocarbons. Carbon is not done yet. It is still going to show you its great properties. Next property which we are going to talk is allotropy. You have studied allotropy in metals and non-metals chapter also a bit. And I think in 7th class or 6th class also it comes. If you don't remember, we would be remembering or not. So allotropy is the existence of an element in 2 or more different forms. Okay. Same element can exist in 2 or more different forms. This property is called allotropy. And these forms of same elements are called as allotropes. Now there are many elements which show allotropy like sulfur. Sulfur exists as rhombic sulfur, monoclinic sulfur, orthogonal. You will study all this in 11th class. Phosphorus exists as white phosphorus, red phosphorus. When it comes to carbon, the carbon forms many allotropes, crystalline, amorphous. You don't have that detail. You have to study 3 allotropes of carbon. They are the crystalline allotropes. So the 3 important allotropes of carbon which you have to study is diamond, graphite and fullerenes. So we are going to study allotropes of carbon. So allotropes of carbon are diamond, which is a precious gemstone, graphite, which is present in our lead pencils. Lead pencils, they don't have lead, it's a misnomer. Graphite. In fact, the word graphite is originated from the word graphon. Graphon is marking over the paper. So graph is actually paper, and when on graph the markings come, it's called graphon, from where the term graphite has come. So it's one of the oldest use of graphite for inscribing, for writing. Okay, and C60. Here you can see the 3 allotropes of carbon. Now allotropes, I go back to the definition. Existence of an element in 2 or more different forms. So carbon is present in diamond. Diamond is nothing. It has only and only carbon. If we have to write down the symbol of diamond, it will be C. That's carbon. Graphite, C. It's carbon. Only and only carbon. Then how are they so much different in properties? Diamond is so expensive. And graphite is not expensive, right? All children all over the world are writing with graphite pencils. So the same carbon which is present in coal, it makes diamond. This is called versatility. Right? In these music shows, they say he is a versatile singer. He can sing this raga also, that raga also. Versatility. So carbon is so versatile. It's forming the coal, it is forming the graphite, it is forming the diamond. So like as a Chemistry teacher also, I think, oh, diamond has only carbon in it. I wonder till now. And that's something to so amazing to wonder about. And that's pure carbon, like computers are versatile. Yes, Rion. Like it has only carbon. Now this graphite pencil, only carbon. So what is that which is bringing the difference? Tell me that difference. Today I will create all the pencils in my home to diamond. So the difference is in the bonding. Bonding of carbon and bonding of graphite is different. Okay. And C60 here that we are going to talk completely separately. So you have to remember these three. So I brought all of them together. So first we should compare between diamond and graphite because these are known to us. Okay. Now when carbon in diamond, when they bond with each other, one carbon connects with 4 different carbon atoms. Every carbon, right, I should say every carbon connects with 4 different carbons. So all the electrons are used up in bonding. In return, these carbons will also be connected to 4 other carbon atoms. Like this. You will not find any free carbon, you will not find any free electron of carbon which has not taken part in the bonding. And due to this, a cage-like structure is formed in diamond. Observe that middle part of this, you can see that the kind of structure it has formed. One carbon is connected to 4. It is showing you just one cross section of diamond. And now you can see this image. Every carbon connected to 4 carbon atoms. This is just one dimensional cross section. You cannot see the entire structure. Okay. So here a cage-like structure is formed, and owing to this cage-like structure, diamond is the hardest substance known. Diamond is the hardest substance known just because of this kind of bonding. There are covalent bonds present, of course, and every carbon is joined to 4 other carbon atoms. Every carbon joined to 4 other carbon atoms. Other carbon atoms. Forming a cage-like structure. Okay? Now, we have to study graphite also, and we have to study about fullerenes also. But it's already 7:30. So I don't want to discuss it today. We will just wrap it up here itself. And I wanted to finish it today, but no problem. We will take it up in the next class. We will begin with the difference in this diamond graphite, or we will start with the allotropy once again. So let's have a quick look what all we studied today. We discussed about the properties of covalent compounds. We discussed that why covalent compounds have low melting and boiling points and they do not conduct electricity. We discussed the uniqueness of carbon where we saw tetravalency. We studied about catenation. We studied about the different kind of possibilities with carbon. We studied the reason for catenation and so many compounds of carbon. One of them is the strong covalent bond also. Now carbon is exceptionally stable and it forms exceptionally stable molecules because of the strong covalent bond, and the reason for the strong covalent bond of carbon is its small size. Small size of carbon. Alright. Next. Quite contrary to others, carbon forms multiple bonds. Carbon exhibits allotropy. These are different allotropes of carbon. We have seen the bonding in diamond. Now this part is incomplete. We have to discuss more. We are done for today's class. Tell me quickly if anybody has any doubt. I'll rush